Welcome back to Calculus 1. I'm Dr. Jeff Groh, and this is your second derivatives lab. We begin with the derivative of x squared plus 2 times x cubed plus 3. Name the rules. You can see that we have here a product and we have power functions. So we will need the product rule and the power rule. Remember, the product rule goes like this. If we have f times g prime, that is f prime times g plus f times g prime. Please remember the product rule in this order. So we proceed. The derivative of the first is 2x. We leave the second factor alone, and then it's plus the first times the derivative of the second. When it comes to the exam, I want you to leave it at this point. The rest is just algebra, and I'll presume that you can do that. On problem 2, we have the derivative of the natural log of x plus 1 divided by e to the x squared. Name the rules. We have a quotient, so there's definitely a quotient rule. And we have functions inside of other functions, so we'll need the chain rule as well. Using the quotient rule, since this is primarily a quotient of two functions, we take the derivative of the top. You need to know that the derivative of natural log of x is 1 over x. I want you to memorize that. But here we have the x plus 1 function inside of the log function. So the derivative of log is 1 over. 1 over what? 1 over x plus 1 times the derivative of the inside. But the derivative of the inside is 1. So this is the derivative of the numerator. Now, times the denominator. Remember, if I have f over g prime, that's the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So it's minus the top times the derivative of the bottom. Now, to calculate the derivative of the bottom, you need to know that the derivative of e to the x is e to the x. But this is not e to the x, this is e to the x squared. So the derivative of e to the stuff is e to the stuff. But I have to multiply by the derivative of the inside, by the chain rule. All of that is over the bottom squared. Yes, we can multiply these and get e to the power of 2 times x squared. And that's fine. But let's leave it at this. On problem 3, I ask you to calculate the derivative of x to the power of x. Now, if I had x to the power of a constant, that would be a power function, and I would use the power rule for calculating the derivative. This is not x to the power of a constant, so I cannot use the power rule. If this were a constant to the power of x, it would be an exponential function, and we know rules for calculating derivatives of exponential functions. But once again, this is not an exponential function. We're going to have to devise a way of bringing the exponent x down. That sounds like a job for logarithmic differentiation. So before we get started on this problem, I'm going to set y. equal to x to the power of x. And then I'm going to take the natural log on both sides. Haven't done any calculus at all here. But by a property of logs, this exponent can come down front, and we now have a mere product rule on the right-hand side. We'll have to take the derivative implicitly, as you always do with logarithmic differentiation. We're taking the derivative on both sides, not with respect to y, but with respect to x, assuming here that y is a function of x, which we know it to be. Which means that when we take the derivative with respect to x, we have to consider this as a composition of functions and use the chain rule. The derivative of log is 1 over, leave the inside alone. But by the chain rule, you must multiply by the derivative of the inside, which is y prime. On the right-hand side, it's a product rule. Derivative of the first times the second plus the first times the derivative of the second. And that's 1 plus log x. To complete the solution, we solve for y prime by multiplying by y and then replace y with x to the power of x. So we get 1 plus log of x all times x to the power of x. And that is the derivative of x to the power of x. On problem 4, we have the derivative of x squared natural log of x over x squared plus 5x plus 6. Name the rules. We have a quotient, and when we take the derivative of the numerator, we have a product. So we have the quotient rule, the product rule, and the power rule, though no chain rule here. In calculating the derivative, we're not going to simplify as we go. The derivative of the top requires a product rule. Derivative of the first times the second plus the first times the derivative of the second. That's the derivative of the top times the bottom minus the top times the derivative of the bottom, which is 2x plus 5. All over the bottom squared. And that's it. Problem 5 is very much like a problem on the exam. Suppose we're taking the derivative of 12/7 times the quantity 4x squared minus cosine squared of 3x to the power of 14/3. Name the rules. We have a power rule and a chain rule, another power rule, derivative of a cosine, and another chain rule. When we take the derivative here, there's actually 2 compositions. There's the square function, and inside of that you have the cosine function, and inside of that you have the 3x function. So 2 compositions means 2 chain rules here plus another chain rule. 3 chain rules altogether. When we apply the power rule, we'll bring the power down. Cancel first. 7 goes into 14 twice. 3 goes into 12 4 times. So it looks like we get 4 times 2 is 8. Just to make that really clear, we have 12/7 times 14/3. Do the cancellations first. Don't multiply first. Students are always trying to multiply first. But that just makes numbers bigger and then you have to work harder to reduce the fraction. No, cancel first. Since we're applying the chain rule, we leave the inside alone. And subtract 1 from the exponent. Subtracting 3/3, we'll end up with 11/3. Then, by the chain rule, we must multiply by the derivative of the inside. The derivative of the first term is clearly 8x. When we take the derivative of the second term, we have to bring the power down, leave the inside alone, subtracting 1 from the exponent, and then we need to multiply by the derivative of the cosine of 3x. That's going to be minus sine of 3x times 3. And that gives us the derivative. I apologize for putting this on 2 lines. And another thing, make sure you get the parentheses right on this. For instance, if you leave the parentheses off here, you'll get it wrong. If you leave the parentheses off here, you'll also get it wrong. You can be guaranteed of something like problem 6 on the exam. You have to be tested over implicit differentiation. Here we have 3x squared y cubed plus 6x y squared plus 8 root x equals 7. Now, we're going to have a bunch of power rules and implied chain rules whenever we take the derivative of something involving y. Recall that if I'm taking the derivative with respect to x of y cubed, I really need to think of that as y as a function of x cubed. So I have a function inside of the power function. You bring the power down and leave the inside alone, subtracting 1 from the exponent, but then you have to multiply by the derivative of the inside. That's why you get 3y squared y prime. Very important that you catch on to that y prime at the end there. If I take the derivative of y cubed, I don't get 3y squared. Not when I'm taking the derivative with respect to x, assuming that y is a function of x. I have to get the y prime. Why? Because of the chain rule. To take the derivative of the first term, we need to use the product rule. The derivative of the first is 6x times the second plus the first, which is 3x squared, times the derivative of the second, which is 3y squared y prime. These two terms represent the derivative of just this first term. Now, on the second term, same thing. Product rule, power rule, chain rule. Derivative of the first times the second plus the first times the derivative of the second. The derivative of 8 root x. Remember, I want you to memorize the derivative of square root of x. The derivative of square root of x is 1 over 2 root x. So you get 8 over 2 root x, and then the derivative of the right-hand side is 0, because the derivative of any constant is 0. We're not done. At this point, we need to move all terms that do not involve y prime to the other side. Factor out the y prime on the remaining terms, and then divide. We'll get y prime equals, we'll have a negative 6xy cubed minus 6y squared minus 4 over the square root of x. On the remaining terms, we'll factor the y prime out. We'll have 9x squared y squared plus 12xy, which we divide off. And so we have our answer. On problem 7, I want you to find where the following function, 3x to the fourth minus 4x cubed minus 84x squared plus 288x plus 1248, where it has derivative equal to 0. Our first step is to calculate the derivative. We'll have 12x cubed minus 12x squared minus 168. Remember to multiply backwards on these. 2 times 80 is 160, and then 8x plus 288. We're setting this equal to 0. It looks like 12 might go into all of these numbers. Does 12 go evenly into 168? To check, note that 12 is 4 times 3. And a number is divisible by 3 if its digit sum is divisible by 3. So 8 and 1 makes 9, and 6 makes 15. Since 15 is divisible by 3, this number is divisible by 3. To determine whether or not a number is divisible by 4, all you have to do is check to see whether or not the last 2 digits are divisible by 4. So in this case, that's 68. 4 goes into 6 once with a remainder of 2. 4 goes into 28 7 times. Since this number is divisible by 4 and by 3, it is divisible by 12. To see what you get, 12 goes into 16 once with the remainder of 4 and into 48 4 times. So 168 is 12 times 14. How many times does 12 go into 288? That's pretty easy. It goes into 28 twice. 2 times 12 is 24. With the remainder of 4, and then into 48 4 times. So this is 12 times the quantity x cubed minus x squared minus 14x plus 24. And we're setting that equal to 0. Since it's all set equal to 0, we can divide the 12 off and not worry about it anymore. We're just solving for roots of this cubic. Now, I'm betting you're not accustomed to solving for roots of cubics. You're much more comfortable solving for roots of quadratics using the quadratic formula. And you don't remember any kind of cubic formula in all likelihood. There does exist one, and also for quartic equations, but not for quintics or higher. There is a simple method for solving for the roots of a polynomial of degree 3, however. What you need to do is use Descartes' rule of signs and also the rational root theorem. Descartes' rule of signs tells you how many positive roots and how many negative roots a polynomial has. A polynomial up to reductions by 2 at a time when they become complex in conjugate pairs. In this case, we go from positive to negative. That's one sign change. Negative to negative is not a sign change, but negative to positive is a second sign change. That means this polynomial has either 2 or 0 positive roots. That's Descartes' rule of signs. That's Descartes' rule of signs. We're expecting there to be exactly one negative root as a consequence. Now, the rational root theorem says that all possible rational roots will be divisors of the constant term divided by plus or minus divisors of the leading coefficient. In our case, the leading coefficient is 1. So it's going to be plus or minus the divisors of the constant term for us. Plus or minus 1, 2, 3, 4, 6, 8, 12, and 24. 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16 possibilities. But as long as we get one negative one and two positive ones, we're done by the fundamental theorem of algebra that says a polynomial of degree 3 has exactly 3 roots, counting multiplicities. So how are we going to solve for the roots of this cubic? There's an easy way called synthetic division. And the way synthetic division works is we set up these coefficients, 1, negative 1, negative 14, and 24. And we'll try these one at a time by plugging them in and seeing if we get 0. But the easy way to plug them in is using synthetic division, as you'll see. By the way, it's pretty clear that 1 doesn't work. I haven't said anything about negative 1, but surely 1 doesn't work. I guess it's pretty easy to see. Negative 1 doesn't work either. So we're going to try 2. We're going to bring the 1 down. This just comes straight down. You bring the 1 down, and then you multiply, and then add. That gives me a positive 1. 2 and negative 1 makes 1. When we multiply again and add, we'll get negative 12. And then when we multiply the 1 last time, we'll get negative 24, and 24 makes 0. Because we're getting this remainder of 0, that's the function value. That means 2 is a root. It also means that our polynomial factors as x minus 2 times the quadratic with coefficients here, x squared plus x minus 12. The rest of this we can do pretty easily. All we have to do is factor a quadratic, and we can do that very well. To factor the quadratic, we'll have x, and then the factors of 12 that will work, 3 and 4, they will have opposite signs, 1 plus, 1 minus, and the larger one will be plus. So we get the following roots, 2, 3, and negative 4. If x is negative 4 plus positive 4 is 0. If x is 3, 3 minus 3, that's 0. If x is 2, 2 minus 2, that's 0. I asked you on this problem to find the x values where the derivative is equal to 0, and we've done that now. We had to factor, we had to use synthetic division, and then just factoring a quadratic. We could have continued to use synthetic division. If we had chosen 3 here, we'll bring this 1 down, multiply and add. Multiply and add. That gives us the remainder of 0 here. We're left with this factor of x plus 4 now. And if we really wanted to, we could try out a negative 4, bring the 1 down, multiply and add. And that gives you this completely done using synthetic division. 2 positives, 1 negative, just as Descartes' rule assigns, implied. We're going to be using these skills in the next chapter, so make sure you understand exactly what's going on with respect to this problem.